All right, folks, it's Bass Action back in action here. In this video, we're going to talk about understanding the solutions to our polynomial equations and then also the factor and remainder theorem. So we're going to start up here at the top. First thing we want to think about is the fact that a polynomial that's of an nth degree, okay, will have it exactly n zeros. Now, real quick reminder on this. The nth degree means that it's either been expanded completely and we found the highest exponent, or we added the exponents of a factored polynomial, all right? Now, that means that our solutions to that polynomial function will be whatever the degree is, okay? So the total number of solutions equals the degree. So if it's a degree 5, you need to find 5 solutions. If it's a degree 12, you would need to find 12 solutions. Those solutions are broken down into 2 categories, real numbers and imaginary numbers. So real solutions and imaginary solutions. The imaginary solutions, we're going to do that one first, will not cross the x-axis. So imaginary solutions occur when we have some type of a polynomial and there's a turn somewhere above or below the x-axis, all right? This would be representative of an imaginary solution. We're going to find those imaginary solutions using our various quadratic techniques. Our quadratic solving techniques will help us find what these are. So think quadratic formula or probably completing the square. Then we're going to have our real solutions, and our real solutions can be written as ordered pairs. If they can be written as ordered pairs, then that also means that they are going to be called our x-intercepts. Okay, so we have solutions that are real and imaginary. Imaginary solutions do not cross the x-axis. Real solutions do cross the x-axis and thus are also called x-intercepts. Those real solutions are further broken down into 2 categories, rational and irrational. Our rational numbers is just any integer, means positive and negative whole numbers, and then also any number that can be written as a quotient of 2 integers. So let's say 1/3, we could say 5/7, anything that is a quotient of 2 whole numbers or 2 integers is a rational number. Irrational things that are like a square root of 3 or a square root of 5 or 2 or pi, those are all our irrational numbers. The rational solutions are going to be found using factoring. Maybe I'll give you a hint. A graph would be a good hint. Intermediate value theorem we'll study later. These are all ways to find rational numbers. The irrational numbers are found using our quadratic solving techniques. Just like we did with our imaginary solutions, we'll find those in the same way. So to summarize this, we're going to want to just remind ourselves that the solutions to any polynomial can be a combination of these types of solutions. They're not going to be all real or all irrational or all imaginary. They might be, but they can be any mix. The most important thing is that the total number of solutions should match the degree. That's how you're going to know that you found everything you need. And then also, irrational and imaginary solutions have to come in pairs. So you can't have an odd number of them. Think we got those from the quadratic formula that had that plus or minus. Now, the factor remainder theorem down here that I'm confident that you did in your Algebra 2 classes. The factor and remainder theorem says that a polynomial, we've studied what those are, has a factor, writing it in its factored form, x minus k, if and only if, this is important from your geometry days, if f of k equals 0. So in other words, if you know something is a factor, then when you evaluate it for that k value, you'll get 0. And then the if and only if says this idea goes in the opposite direction. If you know that when you evaluate your polynomial for that particular value that you get 0, then that k value can be written as a factor. That's how that if and only if works. Now, If the polynomial is divided, so if we divide a polynomial by any binomial that's written in that x minus k form, meaning the leading coefficient is 1 and you're just subtracting some rational number there, then the remainder will be 0, or will be f of k. I'm sorry, I meant to say there. I was looking down at my 0. So our remainder is whatever you get when you evaluate that function for that k value. And the reason I was thinking 0 when I said that is because what we're most going to be concerned about is finding remainders that are 0. Because if the remainder is a 0, then we know we have a factor. That's how this is all going to link together for us. Now, in mathematical terms, this is what the factor remainder theorem looks like down here. Now, this looks really, really complicated, but it's not nearly as complicated as it seems. So we're going to break this down into something that you would have seen in your elementary days. So let's say that I wanted to do 3 divided by 7. Actually, I want to do 7 divided by 3, not 3 divided by 7. Okay. 7 divided by 3. So my f of x is like my 7, and my g of x is my 3. So I'm just going to be thinking about this in terms of these normal, simple numbers. Then, over here on the left-hand side, I'm going to do that long division. So when you were in your elementary days, you would have written this like this. You would have said 3 goes into 7 2 times. You would have multiplied and gotten your 6, subtracted, and gotten your 1. When we write this work in this form, our answer then looks like 2 plus 1/3. So the 2 becomes the q of x. The 1 was our remainder, and that's the r. And then that g of x, remember the g was the 3, goes right here. So this 7 divided by 3 equals 2 plus 1/3. Then in your elementary days, you could have checked that work by then taking that answer, that 2 plus 1/3. If you took that answer and you multiplied the entire thing by 3, the opposite of your division, you would have gotten a 6 plus a 1 that would have gotten you right back to your 7. So then you can see how this all simplifies back out. Our 3, this would become our 3 times our 2 right here. And then here's our remainder. And that gave us our 7, and that got us back. So this 7 was the original f of x that we had. So it's important to just kind of see that this looks really complicated, but we do, in fact, know how this works if we just take it back to something simple. And then in the next video, I'm going to go through examples of how we're going to use the factor remainder theorem.